Now, ito yung previous example natin sa moment diagram by parts. And so there's a way to check if tama yung diagram natin. Diba, in this example, our moment center was B. And so dapat, yung sum nito, saka ito, it should be equal to the moment at B. And then the sum of this plus this one, it must also be equal to the moment at B. And so diba, we can first compute the moment at B. Now taking moments about B, we have 22.143, which is this one, multiplied by the moment arm, which is 3 meters. And then this is plus, kasi clockwise yung rotation. And then we have minus 15, this load, multiplied by the moment arm, which is 1/3 of 3, which is 1. This is equal to 51.429. And then this is K and M. Now, in order to check if these are correct, then we can add, this is our moment center, point B. Let's try to check if 66.429 minus 15 would amount to this value. So press equals, this is 51.429. And so this diagram is actually correct. And then dito naman, for the right side, we have 131.428 minus 80. This amounts to 51.428. And so this is the easiest way you can verify your values right here. Do this before taking the area moments, para sure ka na sa next steps. Now dito, we only chose a moment center about B. Now what if about A? Now copy ko na lang to. What if about A yung kailangan natin? So if about A, this is our moment center. And so let's establish our zero line. Andito yan. And then first, we have to make this load continuous. Kasi diba, yung height ng triangular load is at point B. However, it should be at A for it to be continuous. And so what we have to do is, we need to make this continuous up to point A. And so we'll add this load. So this is now downward. And so diba, this already looks like a uniform load over the whole span. However, since we added the load right here, which is triangular and then downward, we need to counteract this one. So to counteract that, we have to add a triangular load that's acting upward. And so notice that this uniform load is already continuous about point A. Kasi hindi na siya naputol. And then itong triangular load underneath the beam is also already continuous about point A. Kasi diba, yung height ng triangle is at point A. So this is how you can establish continuity. And so diba, dapat yung values ng moments natin aakyat dito sa moment center. And so let's first start with CY. So diba, that will give us 32.857 multiplied by the moment arm, which is 4 times 3. 4 plus 3. So times 7. This gives us 229.999, which is approximately 230. And so dito tayo magsa-start. And then since this is a concentrated load, yung moment diagram by part natin will be 1 degree. So from here, aakyat tayo. We have this value, and then this is 230 positive. Now sir, what is another way to check if it has a positive area or a negative area? If you're holding the moment center and then you're applying the load and then it causes the beam to rotate upward, then it is a positive area. On the contrary, if you will apply the load and it causes the beam to rotate downward, then it is a negative area. So since if you're holding this point and then you're applying this load, our beam will rotate upward, then it's a positive area. That's another way to check. So this is 230. And the next, we'll consider the uniform load. And so our uniform load will have a resultant at the middle, which is 10 multiplied by the distance, which is 7 meters. So 10 times 7, this will give us 70. And so 70 times the moment arm, which is half of 7, this distance, this will give us 70 times 3.5. This is 245. Now, if you're holding this point and then you're applying this downward load, then your beam will rotate downward. And so that means that you have a negative area. So this is 245. However, since this is uniformly distributed, this is 0 degrees plus 2. Our moment diagram by part will be 2 degrees. And so we have a spandrel. This is to the second degree. And then our value is minus 245. Again, this is minus because this will cause the beam to rotate downward. However, we're still not done kasi meron kasi tayong dinagdag na counteracting load. And so we need to include this in our moment diagram by parts. Now you can just overlap the value of this one or you can just create another zero line. Now dati, since hindi ako malinis mag-drawing, then I usually just draw another zero line. And then I will just project a line from here. And then once this is done, idodraw ko na yung moment diagram by part ng counteracting load. Now diba, the magnitude of this load is just equal to 10 kilonewton per meter. So this is also 10 kilonewton per meter. And so the resultant will be upward and then this will be equal to 1/2 times the base, which is 3, multiplied by the height, which is 10. And so this is 15 kN. And then the moment arm will be 1/3 of 3. And so 15 multiplied by 1/3 of 3, which is 1, that'll give us positive 15. Now, since this is upward, and then if you're holding this point, and then you will apply this load, it will cause the beam to rotate upward, then it will be a positive area. So here we have this spandrel, and then this height is equivalent to 15. And so again, just to reinforce the concept, this is caused by the concentrated load of 32.857. And then this moment diagram by part is caused by this uniform load, which we made continuous. And then this additional one is caused by our counteracting load. And so diba, we know that at the ends of the beam, the moment is equal to 0. And so if we're gonna add all of these, it must amount to 0. So 230 positive minus 245 plus 15, this should give us 0. And so this is how you can check. And so to verify if these are the same, this moment diagram by part, saka ito, let's try to solve this area. Itong nasa right side. Just to make this more holistic, isosolve na lang natin yung dalawa. So diba, the area of this triangle is 1/2 times the base, which is 4 meters, multiplied by the height, which is 131.428. And then here we have 1/3 times the base, which is 4 meters, multiplied by the height, which is 80. But this is minus. Again, this just comes from the formula, which is BH over n plus 1. And so let's try to add both. We have 1/2 times 4 times 131.429 minus 1/3 times 4 times 80. We have 156.19. So this is 156.19. This one plus this one. And so dito naman, if you are to add this area and this area, it should amount to this value. Now this height is equal to 32.857 multiplied by 4. So this is 131.428, while this is also 80, minus 80. So diba, these are just the same areas. Kasi this is the same with this moment diagram by part. And so a better way to verify these two is to find the area dito sa left side. And so diba, this yellow area is 1/2 times the base, which is 3 meters, times the height, which is 66.429. And then this pink area is 1/4 times the base, which is 3 meters, multiplied by the height, which is 15. But this is minus. And so 1/2 times 3 times 66.429, this amounts to 99.64. And then this is 3 over 4 times 15. We have 3 over 415. 3/4 times 15, this is 11.25. And this is minus. And so adding both, we have 99.64 minus 11.25, we have 88.39. And so dito, if we are going to add all of these areas, it must equal this value, 88.39. And so let's try that. Now diba, the area of this portion, let's just draw our dividing line, this one. And so this area will be a trapezoidal area, which is, diba, we have a formula, a plus b divided by 2 multiplied by d. And so let's say this is a, this is b, and this distance will be our d. So this area, this one, this is 230 plus 131.428 divided by 2 multiplied by d, which is 3 meters. So times 3, this is 542.142. Now sir, how about this area? To solve this area, we have to get the area of the whole spandrel minus this smaller spandrel. And so diba, we know that this height is 80. Now again, for spandrels, we have BH over n plus 1. And so this is the area of the whole spandrel minus this spandrel. And so for the whole spandrel, we have a base equal to 7 meters. So 7 multiplied by the height, which is 245, divided by n plus 1, in which we have n equal to 2. So this is 2 plus 1. And then minus the area of the smaller one, which is, the base is 4. So 4 times the height, which is 80, divided by 2 plus 1. So this gives us 465. So this is 465. But since this pink area is below the 0 line, then this must be negative. we're just using the absolute values for the value of the area, but you need to consider the sign. Now for this one, we have a triangular load, so this is to the third degree, and so this area will be 1/4. Again, we have n plus 1 times the base, which is 3 meters, multiplied by the height, which is 15. And so this is now 1/4 times 3 times 15. We have 11.25. So 11.25. And so adding all of these, we have 542.15 minus 465 plus 11.25. We have a value of 88.4. So this is 88.4. And so diba, this is the same with our value right here. Meron lang discrepancy due to the rounding off of values. And so this is one way you can check. Now sir, how about if about C? If our moment center is about C, how can we make the load continuous? First, yung height ng triangle, this triangle, must go to C. And so you will need to extend this one up to the moment center. Now again, this is about C. And then diba, essentially, this is now a triangular load over the whole span. But since we added a triangular load right here, then we need to counteract that. We have to add another triangular load which is acting upward. And so once you have this, you can now draw your moment diagram by parts. If this is our moment center, then we have this for the concentrated load. And then for the triangular load, by the way, this is actually downward. For the triangular load, we have this figure. So this is to the third degree. And then to get this height, you just need to apply ratio and proportion. So diba, for this large triangle, we have a height of, let's say, W. And so W is to 7, which is the whole base, equals 10 is to a base of 3 meters. And so this W will be x over 7 equals 10 over 3. We have 23.33. And then this is Kn per m. While for this one, the magnitude of the triangular load must be equal to 23.33 minus 10. Now again, this is 10. And then this whole height is from here, let me just move this. From here up to here, we have a height of 23.33. And so this value is 23.33 minus 10. So this is 13.33. And so the height of the triangle is also 13.33 because we are only counteracting this load. And so here, you will need to add another zero line for this triangular load which is acting upward. And so let's project a line here, and then we'll have this figure. This is upward, so positive. And then this is for this triangular load, the counteracting load. And so the value of this one is 22.143, this load, multiplied by 7, which is 155.001, or approximately 155. And then for this one, this is for the whole triangular load over the whole span. And so this will have a resultant of 1/2 times the base, which is 7, multiplied by the height, which is 23.33. So this gives us 81.65, or let's say 66. And then our moment arm going to C, that will be 1/3 of 7. So 1/3 of 7. Now again, this is our whole base. So this load multiplied by 7/3, we have 190.528 or 53. So this is minus 190.53. Now again, if this is our moment center, we'll be holding that point. And so if we'll apply an upward force, then it will cause our beam to rotate upward. While if we are applying a downward force, it will cause our beam to rotate downward. And so that's why this is positive and this is negative. And then this upward load will also cause the beam to rotate upward. Let's say you are holding this point and then you're applying this resultant force, the beam will rotate that way. So that's why this is also positive. Now the value of this resultant will be 1/2 times the base, which is 4, multiplied by the height, which is 13.33. And so this is 26.66. And then this moment arm is 1/3 of the base, which is 4 meters. And so multiplying this one by the moment arm, which is 4/3, this one, we have 35.55. And so this is 35.55. And then if we'll add all of these, since this is at the end of the beam, then this should amount to 0. And so 155 minus 190.53 plus 35.55, we have 0.02, which is approximately 0. By the way, the degree of this line must be 1 because this is for the concentrated load. So 1 degree, while this is also to the third degree, because this is for the triangular load, this one. Now if you want to verify this moment diagram by part, then you can actually solve this area plus this one. Now the total of these areas must be equal to this area. Now we know that for this one, if you will add both of these, 1/2 times 4 times 131.429 plus minus 1/3 times 4 times 80, we have 156.19. And so let's just copy this one, and then let's move that here. Let's try to solve this area. Now by ratio and proportion, we can get this value and this value. So for the triangle, we have 155 is to a base of 7 meters. That's equal to y, which is, let's say this value, is to a base of 3 meters. So we have 66.429. So 66.429. And then for the bottom one, we can consider this strip, and then we can take moments about B, or we can just use ratio and proportion for this spandrel. And so we have, for the whole spandrel, we have a height of 190.53. That's to a base of 7 meters. However, since this is on the third degree, then we need to cube this one. Again, for the relationships of triangles or spandrels, we have height divided by base to the power of n. Now since n is 3, then we need to cube this one. Now this is equal to this height, which is, let's say, let's just make this y1 and this one y2. So for y2, we have a base of 3 meters, and then we'll cube this one. So solving y2, we have 190.53 over 7 cubed. This is equal to y2 divided by 3 cubed. And so solving x, we have 14.99, which is approximately 15. So this is 15, and then minus, since we are below the 0 line. And so if you're going to solve this area, then we have, for this area, let's just use the formula for trapezoidal shapes. So this is a plus b divided by 2 times d. We have 66.429 plus 155 divided by 2. We have to multiply this by 4 meters. And so this is 442.86. And then for the bottom one, for this area, we need the area of the whole spandrel minus this smaller one, the same as earlier. And so for the whole spandrel, we have a base of 7 meters times a height of 190.53 divided by n plus 1, which is 3 plus 1, and then minus this smaller spandrel, which is 3 meters, our base, multiplied by the height of 15 divided by 3 plus 1. And so this gives us 322.18. And then for this one, we have BH over n plus 1. This is 4 meters times 35.55 divided by n plus 1. We have 35.55. And then by the way, this is minus because we are below the 0 line. And so 442.86 minus 322.18 plus 35.55, we have a value of 156.23. So 156.23, this is approximately equal to this one. However, the discrepancy is just the result of the rounding off of values. And so just to add other examples, if we have this load and then we want to make it continuous about C, then we're gonna extend this load. And so essentially what we are adding is a trapezoidal load. And so here, we'll counteract that with also a trapezoidal load. This is about C. Now for this loading, if we want to make it about A, then we can first make this a uniform load by adding a triangular load. So this is now uniform, but we need to counteract this one. So we have upward. And then notice that if our moment center is about A, then this still isn't continuous about A. And so we need to extend this one, this uniform load, and then we'll need to counteract this load. So let's add a uniform load here at the bottom. And then now, since the triangular load is not continuous about A, then we need to extend this one. And so let's just use another color. We have to extend this one up to here. And then since we are adding a triangular load which is upward, then we need to counteract this one with a triangular load acting downward. And so notice that if you don't know how to choose the moment center, then it will be very difficult to draw the moment diagram by parts. Now the easiest moment center for this figure is about C, while for this one, the ideal moment center is about B. For this figure, the ideal moment center is about B, while for this one, it may be B or C. And then for this figure, we need our moment center to be at B. Now as a challenge, try to make this load continuous about point D. Just apply this concept and also this concept.